All right, so we're going to look at a little bit from section 11.7 before we go on to power series. And 11.7 is strategies. In other words, when we look at a series, we want to have an idea of what to do. Well, first off, I want to remind you about sizes. Excuse me. Exponential functions are bigger than any polynomial, and by degree, n to the fourth, bigger than n cubed, bigger than n, bigger than n squared, bigger than n. And then now the n to the p's, they're even smaller than the n's, and they all fit in there. These are all bigger than logarithm, and the logarithm is bigger than constant sines, which is like sines and cosines. In general, you want the bigger things on the bottom, smaller things on the top, to hope for convergence. If it's the other way around, it's impossible. So for example, when you have e to the n over n squared, if you were to sum this right away by just looking at the sizes, you go, wait a second, it's big on top, small on the bottom. You expect this to diverge. That's just by using the size look. Then you take and look for a divergence test. For example, integral tests show it diverges, or just show that the limits of the terms doesn't get small. Now, sizes help, but they aren't always the perfect way to do things, because take, for example, n squared over n cubed plus 2. Well, n cubed is bigger than n squared, so these terms are going to get small, but it turns out this is just too much like 1 over n, which doesn't converge. And so just because you know the bottom is bigger doesn't mean that you're necessarily going to get convergence. Now, the basic ideas is that when you see a series, you might ask yourself, what's its size? So consider this series. Well, 3 halves is 1 1/2. That's bigger than n, so this is the biggest term in the top. Biggest term in the bottom is n cubed. And so this is like an n to the 3 halves over an n cubed. Well, using power rules, 6 halves minus 3 halves is 3 halves. And now this is looks like a p series, and p is bigger than 1. So this looks like a convergent one. So you know that you found a basic comparison. You might do a limit comparison or a straight up comparison on this to show that that's less than some multiple of that, or that the limit of this divided by that, or vice versa, is a constant. Now, there are some functions that are special. The n factorial function is one of them. So let's do 2 to the n over n minus 1 factorial. What should we do with this one? Well, first off, I didn't put this on the list here. Turns out that factorials are even bigger than exponentials. So right off the bat, this looks really good for convergence because it's big on the bottom. But which test should we use? Well, the nth root test is the strongest test, and that can get rid of the 2 to the n, but nth roots of n factorials are a little bit messy, and we haven't covered those. This one is set up for the ratio test. Why would we use the ratio test? Because when you calculate an plus 1 over an, factorials and powers are specially attuned to being able to use a simplification algebra that takes place in the ratio test. Now, a couple of series just scream at you. When you see a series that somebody asks for, find the exact value of. Well, when they see the words exact value, then there's really only 2 choices. This has to be a geometric series. Somehow you can write it this way, or it's a telescoping series. So if you can't make it look like one of those 2, then the question itself might be very difficult. But in general, the geometric series and the telescoping series are the only ones that at this moment we can find their exact values. Now, another series that's nice to spot is when you have a minus 1 to some power. And let's put it over e to the n. Well, this is set up for the alternating series test, where we just have to take a limit of the terms and see if they get small, and we can conclude convergence or divergence. is very powerful to know a way to start. Now the ones that get a little tricky are things that look like this. We throw a log n, and let's say an n to the 1/2 plus n. And you might go, well, what in the world am I going to do with that? Well, if you go back to this list, the log n, it's smaller than n. So it is not, however, it is bigger than a constant. So it looks like this is bigger than some constant over n. And so by ignoring certain pieces and saying, wait a second, that's bigger than the constant, so this is bigger than that, and this basically should be made bigger than that, it looks like we should be able to prove that that thing diverges. These are the types of things that we want to attempt and we want to work with. We ignore certain pieces, we look at just the relevant part, and then we attempt to apply a test. Now, there are a couple of terms that cause some difficulty for the students, and that is when we have sequences that contain plus or minus signs, so the series is probably only going to be evaluated with an absolute value. So if you have a sum like this and you end up saying, I'm going to look at this, and you discover that this diverges in their absolute values, but converges over here, if you've done a lot of work somehow, why you looked at this if you knew that converged, who knows, but if you discovered that that was divergent and that was convergent, this is a special case. This is where the sequence really needs the minus signs to be convergent. And an example of that is minus 1 to the n over n. This, when you have the absolute values, is a divergent sequence. But because it's an alternating series and its limit gets to 0, it's convergent. This is an example where the absolute value diverges, but it converges with the minus sign. This is called a conditionally convergent series. It's conditioned on keeping the minuses. And they're somehow special, and they occur fairly frequently, but it's a vocab that we need. All right, that's some methods to use for addressing series. It's now time to get kind of cool. This is section 11.8, and what we are doing, we are heading for a very powerful thing. We're heading for being smarter than our calculator. Our calculator's got these keys, sine x, cosine x, tangent to the x, e to the x, log x. All of these keys require rules that are actually infinitely long to calculate things, and these rules come from something called a power series. And I think it's kind of cool it's called a power series because they are very powerful. But a power series is really a form of a generalized geometric series. The geometric series looks like this, r to the n, or it may have a constant multiple in front of it. That's the geometric series. And we know their exact values. But if we let the terms vary with the power, something special happens. A power series has some starting point. It's an x to the n, goes forever, and we can choose set values of x. This is called a power series in x. Now, I'm going to give you an example of one. So if I let an be minus 1 to the n over n factorial and x equals 2, then this would read the sum of minus 1 to the n over n factorial 2 to the n, and now this is an alternating, and let's have some starting point. Let's start at 5. Then this looks like a series that we've looked at before. It turns out the alternating series test is sufficient to show that when the limit 2 to the n over n factorial goes to 0, that causes this thing to converge. Now, because we know that that thing converged when we put in x equals 2, maybe it also converges when x equals 3 or x equals 4. And so it's very useful when we have these series to not fix a value for x, but see if there's some test that tells us, given this power series, is it possible that I can determine for which values of x the series is going to converge? Now, simple series put in front produce simple power series. So for example, this says every coefficient is going to be 1, and it's just 1 plus x squared plus forever. That's the geometric series where we replaced r by x. And the answer is it's 1 over 1 minus x if we have small enough values of x. Now, it clearly doesn't make sense to put in 1. It gives us infinity. And it is weird to put in minus 1, because when we put in minus 1, we get 1 over 2, 1/2. And 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever. It doesn't converge, yet this thing gives an answer. So we have to be very careful when we talk about what values of x a power series produces convergent answers. But the geometric series, that's what it looks like when we use x's, and it'll work for any value of x between minus 1 and 1. All right, let's take a look at another power series. This one is also going to be a geometric series. This is a power series for r equals 1/2. But it's also a power series, geometric series with r equals 1/2, but it's also a power series evaluated when x equals 1/2. So even though we have more than one name for a series, it turns out this is more flexible, because this looks like that, but that's the standard form that we use to write it. So now, let's write down some funky power series, and let's see if we can determine if it converges or not. So let's try this one. Let's take the sum of x to the n over 2 to the n equals 0 to infinity, which is 1. And we put in 1, we get x over 2. When we put in 2, we get x squared over 4. And the bottoms are doubling. Wouldn't it be nice to know which values of x we could plug in here to make sure that this thing is convergent? Now I want you to notice, I'm going to go to the side here, and if x equals 1, this is just a series of 1 over 2 to the n, which we know is a power series, a geometric series, and it converges. But if we put in x equals 3, now this is a geometric series with r bigger than 1, and we know it diverges. So there is a question of which x will make this thing convergent or divergent. Well, I'm going to apply the ratio test to this. I'm going to calculate an plus 1 over an, absolute value. So I'll get x to the n plus 1 over 2 to the n plus 1, divided by x to the n over 2 to the n. An plus 1 over an. Invert and multiply. And now 2 to the n plus 1 on the bottom and 2 to the n on the top. We'll leave a single 2 in the top. X to the n plus 1 on the top. X in the bottom. We'll leave a single x in the top. And we're going to discover that our ratio test produces x over 2. And now if we take the limit as n goes to infinity, there's no n's left. This is the answer. And the ratio test said this will converge if this is less than 1. Well, we can draw a picture of that. X all the way up to 2 and x all the way down to minus 2. Here are the values of x for which this series converges. Now, it turns out we're going to learn to check the endpoints of power series as well, but for the time being we can see here are places of clear convergence. Now, there's also the ability to spot greater than 1 here. If this was greater than 1, that's this region, and this region. And that's why I said these 2 points, x equals minus 2 and x equals 2, might be special. Do they belong to the convergent or do they belong to the divergent part? But this is how we're going to work with power series. We're going to ask for what values of x will these things converge. Now, sometimes power series can be manipulated a little bit. So now I'm going to write down a power series that doesn't quite look right. It looks like I'm using the x wrong. So watch this one. Let's do this one. X minus 2 to the n over n factorial, n equals 2 to infinity. For what values of x does this converge? Well, first off, I want you just for a moment to think, oh, let's don't worry about x minus 2. Let's write it as t to the n over n factorial, n equals 2 to infinity, where t represents x minus 2. All of a sudden, it looks like a power series, but using x in its place. I'm going to apply the ratio test on this. I'm going to take t to the n plus 1 over n plus 1 factorial divided by t to the n over n factorial absolute value. There's the n plus 1 term divided by the n term. Invert and multiply. And t to the n plus 1 over t to the n, why that produces a t, an n factorial over n plus 1 factorial, just so you see it enough. N plus 1 factorial is always take one of the n plus 1's off. What's left, it goes away. And so we get t over n plus 1. And now if we take the limit as n goes to infinity of this, t is a fixed value. It's going to be some number. Guess what? This goes to 0. So this is a strange situation. No matter what the value of t, this always converges. No matter what the value of x, this always converges. This converges for every value of x. Oh my goodness. It's a series that doesn't matter which x you put in, it's going to converge. Now, why did that happen? Well, because an exponential, something to a power, is always less than a factorial. Now, let's do another one of those, but make it actually converge for a limited value of x's. Again, these x's can be made to look very strange. Again, that looks like I'm using the x's wrong, but something to a power over with an a sub n. Now I'm going to use the ratio test again. By the way, the ratio test is the #1 used test when you're working with power series. So I'm going to do a ratio test on this one. an plus 1 over an x minus 3 to the n plus 1 over n plus 1. I plugged in n plus 1 divided by, plug in the n, absolute value, invert and multiply. Now here's an x minus 3 and an n, and up there is 1 as well. So we still have an x minus 3 to this first power left, and there's an n and an n plus 1 there. Now we're going to take the limit as n goes to infinity. Now what's interesting here is that's constant with respect to n, so the x minus 3 pops out inside of an absolute value. But the limit of n over n plus 1, using the standard trick of multiply by 1 over n, this goes to 1, and our answer is the absolute value of x minus 3. So the ratio test tells us this series will converge if the ratio test is less than 1. Now, from Calc 1, you should be good at knowing what this looks like, but if not, I'll remind you. It's an interval, centered at 3, radius 1, and so we know for certain that we have convergence inside of here because the ratio test is less than 1. And if it was greater than 1, we know we have divergence, so it's diverging out there. And what's left is we have the question of what is happening here. Is it going to converge or diverge at the numbers 2 and 4? So this is how power series are worked with And what's really neat about power series is that power series are going to be used to be the rules for exponential, logarithm, square root functions. Power series are going to be the rules that tell us how functions behave. Now, as you just saw here, this interval here makes a given power series have an interval of convergence. There's always a center and some radius, and then the question is, do the endpoints actually work in there? And outside of that interval of convergence is divergence. And this is a special property that every single power series has. Now, a couple of power series are strange. The interval of convergence has sometimes r equal to infinity. We saw that one. And that means we say the power series converges for all r. That says the power series is really good. So power series can have finite intervals. We'll take a look at how endpoints get involved. We can get things like this. We can pretty much get everything you can imagine. And so this is the intervals on which power series converges. All right. Now, what are we going to do with power series? Well, the first thing we're going to do is we're going to write down some power series, and we're going to figure out the intervals of convergence, and we're going to figure out good values of x, and we're going to check their endpoint. So let me do one. Let's do this one. The sum of x to the n over n to the fourth, 4 to the n equals 1 to infinity. Now, the big thing about power series is that we love the ratio test. It's quick, it's easy, and you'll learn very quickly that you don't have to write the fraction over fraction. You just invert and multiply immediately. Next thing is you learn that the powers always do nice things. The n's always nicely work together. Exponents always nicely work together. And now when you want to take the limit as n goes to infinity, you're going to remember the neat little trick that when you multiply top and bottom by 1 over n to the fourth, that limit is going to go to 1. And these things become nice and simply statements like this, where absolute value of x is less than 4, which says this is a power series that converges, centered at 0, goes all the way up to 4, all the way down to -4, and these are the values that it converges at. And I'm now going to check the endpoints. So I'm going to check the endpoints of the interval of convergence. I am going to plug in x equals 1 and see what x equals 4 and see what I get. So the sum of 4 to the n over n to the fourth, 4 to the n. Why, that's a sum of 1 over n to the fourth, which by the p-test converges. So we just discovered it converges at 4. So now we're going to plug in x equals -4. We have the sum of -4 to the n over 4 to the n to the fourth. Why, that is -1 to the n over n to the fourth, and that's an alternating series, and the limit as n goes to infinity of 1 over n to the fourth goes to 0, and that's the alternating series test that says it converges at 4. So this series converges on -4 up to 4, and it diverges out of there. This is power series. And we're going to start developing power series and learn that we can do every button on our calculator that has a function associated. All right.